Hello, this is an educational session for SMRT number E7859 Magic Angle Directional Imaging MADI, presented by Karen Chappell. I have no financial interests or relationships to disclose. How do you go from a discussion with a leading medical physicist making napkin notes in a coffee shop near Chelsea's Kings Road to presenting at ISMRM and an MRM publication? Why not grab a cup of tea or coffee and spend the next 25 minutes hearing about that journey, plus revising some of the key principles, but also maybe learning how to see a pesky artifact in a new light. That artifact is the magic angle effect, which is an intriguing conundrum. It could offer so much as a new contrast mechanism, but mostly offers clinicians confusion. It's viewed as a hindrance because it mimics pathology, has been revisited time and time again, especially after advances in MR scanner technology, only to be thrown in the dustbin when something easier comes along. That's basically what happened to me. My journey actually began sometime earlier during my first MR research job, where we were trying to scan rheumatoid arthritis patients at the magic angle by contorting them into highly uncomfortable positions inside MR scanners. As you can imagine, it wasn't particularly practical nor very well tolerated. But that is all that's really possible inside our current MR systems, as the magnetic field, the B0, is fixed. It depends on the configuration of the scanner, either the horizontal field, the vertical field, or a transverse field system. But as you can see from these images here, you're always going to be limited due to the close confines of the sides of the scanners. The other issue with our conventional systems is the fixed coils, which really need to be aligned with the main magnetic field for optimal image quality. So how do you scan a patient harnessing the magic angle effect? One of the initial ideas was to make everything move: the patient, the magnetic field, and the coil. Like the gyroscope shown here, gyroscopes have 2 or 3 gimbals so that the spin axis is free to assume any orientation by itself. How many gimbals are in this example? Basically, gimbals are just pivoted supports that allow rotation of an object around a single axis. With 3 gimbals mounted together, each will offer a degree of freedom, so you get the yaw, the roll, and the pitch movements. This example has 2 black rings or gimbals. Not being a fan of upside-down spinning rides nor vomit, I was very relieved when we agreed not to spin the patient. The prototype scanner was designed with a permanent transverse field magnet and 2 degrees of freedom, or 2 planes of rotation, yaw and roll. The roll axis has a full 360 degrees of rotation, whilst the yaw axis had plus or minus 35 degrees, allowing for multiple combinations of orientations in order to cover the entire joint. The limiting factor of the yaw rotation will be the patient's limb, which will go between the 2 parts of the magnet. As the prototype was being built, everything needed to be worked out on conventional scanners in preclinical models first. That meant just scanning legs. Lucky for me was that goats' legs do not develop spontaneous arthritis, so I could figure things out in a healthy model. The prototype scanner was designed for extremity work, so we chose to focus on the knee joint with its majority of short T2 tissues. MRI permits direct imaging of soft tissues, but collagen-rich tissues such as the menisci, tendon, ligaments, plus articular cartilage to a certain extent cannot be measured by conventional MRI, as there is a rapid relaxation of the MR signal so that the tissue often appears dark grey or black. You can see that in the tendon's T2 decay curve here, where the MR signal has decayed before it can be made into an image in the data acquisition window. When short T2 tissues are positioned at the magic angle, their T2 is lengthened, giving you more time to collect the signal. And you can see here that the signal hasn't decayed anywhere near as fast, and there still remains some to be made into an image. Okay, let us begin by reviewing the magic angle artifact. If you think magic angle, you think 55 degrees. It's a bit of a myth that the increased signal intensity only occurs at exactly the 55 degrees. This is when signal intensity peaks or is at its highest. It is at its lowest at 0 and 180 degrees, but in low TE sequences, an increase in signal intensity can be seen in angles ranging between 40 degrees and 65 degrees. Only collagen-rich tissues are involved, as it is an angle-dependent problem caused by the angle that the collagen fibers make with the main magnetic field be 0. The magic angle effect has been demonstrated in a wide variety of highly ordered collagen-rich tissues such as tendons, ligaments, peripheral nerves, enthesis, invertebral discs, menisci, articular cartilage, to name a few. It is the most noticeable when structures like tendons curve around corners like in the shoulder, wrist, ankle or knee. This knee example shows the magic angle artifact as an increased signal on the short TE PD image, and that's within the patella tendon around about the level of the tibial tuberosity. The tendon itself is not thickened and has a dark signal intensity on the long TE fat image, helping to distinguish the artifact from injury. But if you look closely, you can still see a slight increase in signal within that black tendon sheath on the TT fat sat. The problem with the magic angle effect is that it's an inherent tissue property. You can reduce its visibility on clinical scans by altering the parameters by, say, increasing the TE, altering your patient position, using multiple sequences and slice orientations. However, you cannot get rid of it completely. Any sequence that exhibits a T2 decay term will experience the magic angle, and that includes sequences such as diffusion, T1 row, T2, stir, UTE. We normally only associate the magic angle effect with T1 or proton density weighted sequences. Okay, let us revise dipoles so that we can start to understand the underlying principles. Protons, electrons, and MRI nuclei with odd numbers always have an unpaired proton, which creates a net magnetic field or magnetic dipole moment. A magnetic vector is called a moment and is denoted by mu. There is always two poles, which is what gives you the dipole. The north pole of the magnet is defined as the origin of the magnetic field lines, and the south pole is where the magnetic field lines return to. When the field lines from two magnetic dipole moments cross, a dipole-dipole interaction occurs. Dipole-dipole interactions are the single most important mechanism for T1 and T2 relaxation. Alright, on this slide, I've changed the magnetic field lines to positive and negative fields surrounding the magnetic dipole moment. The red dot indicates the position of a second nuclei. Its local magnetic field at a distance of r, which is the green dotted line, and at an angle of theta from the magnetic dipole moment mu is calculated. The z component of the dipolar field is the b mu z, maximally positive directly in front of that dipole and maximally negative on either side. In this example, the second nuclei is between the positive and the negative fields, so the b mu z passes through a null point equaling 0. This occurs at an angle where 3 cosine squared theta minus 1 equals 0, the magic angle. And these occur at approximately 54.7 degrees, 125.3, 234.7 and 305.3, and you can see that basically it's the area, those null points in between the positive and the negative fields. In this slide, we're going to try and relate what we've learnt to the molecular collagen structure. So here you can see some triple helix and the hydrogen bonding, or the bonding of the water onto those triple helix. The proton interaction occurs along the same axis as the collagen fibre. So when the collagen fibre is orientated parallel to B0, the dipolar interaction is maximal, leading to very fast T2 relaxation times. The relaxation sink for the entire water-proton system is primary hydration of the polar sites on that main chain. When the collagen fibre is orientated at the magic angle, the dipolar interaction from the static field falls to a minimum. This lengthens the relaxation time, and that's because the T2 decay is only governed by the time-varying field. Developing magic angle imaging for a whole joint is very complex. The literature describes mainly single excised tissues. The problem is that multiple tissues have different anatomical positions and multiple fibre orientations that all must be orientated to have a magic angle effect. When positioning a limb, there is no way of knowing the alignment of the collagen-rich structures, as they are hidden from view and cannot be palpated. That is why a whole goat knee was scanned at different horizontal angles to B0, and regions of interest were plotted to determine the signal intensity variation for different tissues. Interestingly, some tissues at the 0 degrees, which is the position we would normally scan patients in, actually are exhibiting a magic angle effect. That previous experiment was performed on a horizontal field scanner. You can see here from this slide that the anatomy positioned at the magic angle will be dependent on the field direction of the MR scanner system being used to create the images. In order to create the MADI technique, we had to rip up the rules and start again from scratch. So to do that, we determined which pulse sequence gave the greatest magic angle effect, how many directions do we actually need to scan in, and how do we get something meaningful out of the data? Reviewing the literature to learn how to remove a magic angle artifact proved useful in optimizing proton density and T1 weighted 3D pulse sequences. For MADI, we actually selected a T1 flash sequence as it provided the greatest magic angle effect in the fastest time. And this was an important consideration, bearing in mind we would need to repeat the sequence multiple times in multiple directions. So, how many directions? Luckily for me, two groups had attempted similar work before, but neither had developed a mathematically robust way to determine the optimal number of scan directions. Both had scanned in the orthogonal planes, which was much easier to perform experimentally, but creates very similar scan positions. And in the case of the 3 orthogonal planes, it actually created gaps so that the whole sphere wasn't fully sampled. We postulated that a minimum angle between B0 must be maximized so that the scanning orientations needed to be equispaced in 3D. Mathematically, that actually turned into quite a difficult problem to solve. We used the Leopardi solution, which partitions a sphere into regions with equal areas before running simulations with 15, 9, 7, and 5 scan directions. The more scan directions means the longer the patient will be inside the scanner. It's important for you to note that the work presented here was actually performed on an animal knee obtained from the local butcher. The experiments to determine the optimal number of direction were performed using 15 orthogonal directions and 9, 7, or 5 equispaced in 3D. Then a patella tendon was selected to compare the different numbers of directions using a segment from a single slice through the patella tendon, which consisted of around 100 voxels. The scan times are shown on the right. Clearly, they're still far too long for a patient examination, but they don't involve any speed-up type processes such as parallel imaging, SMS, or anything along those lines. We compared everything with the 15 orthogonal directions, and you can see that actually 9 directions were optimal. If you look very carefully at the fibre orientation maps of the patella tendon, you can actually spot differences. 7 directions is the minimum needed, provided that there is no noise. The more noise, the more that this data is actually affected. And 5 directions is just insufficient to compute the collagen direction. You'll notice in the 15 directions that there's a couple of voxels shown towards the edge, and this is due to the blurring that tends to happen with the registration and alignment. The more directions and volumes that you need to register. There isn't enough time to go through in great detail the post-processing. This slide covers the main steps. Firstly, we registered and aligned the 9 volumes. Then we created magic angle contrast or standard deviation maps. Then we segmented by thresholding for voxels demonstrating the greatest signal intensity changes. Net vector orientation maps were computed using MATLAB. Collagen fiber tracks were then visualized in ParaView, and the alignment index was computed for each of the collagen fiber orientation distributions, and that's visualized on a hemisphere. After developing the MADI technique in a healthy model, we needed a proof of concept study to ascertain what happens in damaged tissue. Torn ligaments and degeneration may disrupt the contrast mechanism, decreasing tissue anisotropy. Dogs develop similar health problems to their human owners. For example, these 4 breeds are more prone to suffering with problems such as ACL ruptures, osteoarthritis, and meniscal injuries. In conjunction with the Royal Veterinary College London, ethical approval was granted to include in the study larger dog breeds euthanised at the vet hospital where owners had given permission for a post-mortem examination. The knees were scanned on a 3 Tesla MRI scanner in the head coil using the 3D T1 flash sequence at 9 orientations to the magnetic field. Volumes were registered and aligned before standard deviation maps were computed to identify collagen-containing voxels. An interactive display was used to measure the standard deviation ranges of voxels and segment areas with higher standard deviations. The net collagen orientation of the voxels was displayed as fiber orientation vector maps and ParaView vector glyphs in 3 dimensions. Finally, knees were dissected and photographed by the vet. During a 6-month data collection period, 10 knees were included in the study. 2 were found to have ligament pathology, which was identified by the vet during the joint dissection. Here are some post-mortem images which show the shiny, healthy ligaments on the left and the partial rupture of the anterior medial band on the right. In the ParaView fiber tract images, on the left, continuous fibers can be seen running through the healthy ligament, and on the right, there's disrupted fibers in the anterior medial band, indicating the partial rupture. The posterior lateral band can be seen behind. This is our alignment index, which is abbreviated to AI and now keeps being confused with artificial intelligence. It computes the collagen fiber orientation distribution and then visualizes that on a hemisphere to help us to detect changes within the ligament. Dark red shows the most aligned fibers and dark blue shows the least aligned fibers. In the healthy knee on the left, you can see a discrete bundle that corresponds to the anterior medial fiber bundle. When you compare that to the damaged knee on the right, you can see that the actual anterior medial fiber bundle is disorganized. It's smeared right the way across from medial to lateral surface. The posterior lateral fiber bundles in both knees are undamaged and highly aligned. So our proof of concept study was a success and proved that the MADI technique worked. If you'd like to learn more about this work, please visit Digital Poster Presentations 2802 and 2803. The translation of scientific advances into clinical practice can occur very fast or take decades. The magic angle effect was first described in 1962 by Berenstain. Its potential for providing detail inside short T2 tissues like ligaments is finally becoming clear. Hopefully, once the technology catches up, it will revolutionise the way we assess and treat musculoskeletal injuries. Finally, I would like to acknowledge all these wonderful people who made the Maddie work possible. Thank you.